Yeah, so you guys can hear me in the back? Good? Okay, cool. So yeah, I like to write databases in my free time. It's kind of a weird hobby to have, but I really like writing them in Go, and it's just, Go's just a fun language to write stuff in. So this is about writing high-performance databases in Go. So before we really get into this, let's talk about, when people say they write a database, there's really two different things they're talking about. You can either have a database server, so this is kind of where you model your data. This is like MySQL, Oracle, it's a document database, it's a relational database, and it runs in like a separate program. It's its own thing, separate app. And then, you have some kind of network API to get to it. And that, I wrote a server called Sky, which does behavioral analytics. So you take event streams in and you can analyze them. And then there's a database library, which is really where you have it inside of your program itself. It's real low level, and database servers typically use database libraries as well. So you have like LevelDB, LMDB, BerkeleyDB, and it handles all this stuff like blocks and pages and like little nitty-gritty details. So I wrote another library called Bolt, which is more in this vein. So despite those actually both being called databases, they're totally different things to write and interesting in their own right. And you might think that this doesn't really apply to you guys because you're never going to write a database, but ultimately we all access data. That's what our programs do, and just databases are this very pure form and like a very isolated kind of use case for it. So there's a lot of things you can kind of really figure out about your programs and how to optimize them. So the hardest part about writing databases in Go is that you get asked this question all the time, like, why'd you write it in Go? Which is a big pain. People always think you should write it in C, write it in Java. They're kind of the standard languages. But when I actually started writing Sky originally, I wrote it in C, and I wrote it once, and then I rewrote it, and wrote it again, and just rewrite after rewrite. And the thing I realized is there's a lot of my code doesn't actually need to be run like blazingly fast. Like things like adding a user doesn't need to be like screaming fast. But they have this bucket of all these things that are actually, just need to be pretty fast, and then things that really need to be like really darn fast. And you have query execution. That's really your main thing you're looking at when you're trying to get data out of your database. You have large volumes. Most applications are read intensive. So it's really where you want to optimize. Obviously, this depends on your workload as well. So different databases have different trade-offs, but I would say most applications are very read-heavy. So your mileage may vary. And there's also another thing that databases aren't just about speed, like raw power. We're getting cheap hardware, cheap RAM, all that stuff. Other things like easy deployment, like we have Docker. There's a whole ecosystem around just Docker and how to deploy stuff easier. You have things like user-friendly APIs. JSON over HTTP is a huge pain when you're trying to do C. It's rough. And just simple debugging. You go to Go, and you get a nice stack trace. What's going on in there. Great profiling tools. You get some stuff in C, but it's a little rough. But you still have this question of, how do you make those fast parts really fast? So, the easiest option you can do is just write it in C. That's kind of the cheat way to go. And this is the way I went with Sky originally. So the plus side of this is you get all these libraries. There's tons of code out there that people have already written that you can just take and just plug in and just run with. And then the downside is, one of several, is that every time you hit C, you get an overhead. There's like a wrapper function that you have to go through to get to your C calls. So you can't call that millions of times a second. You need to kind of dump off all your processing to C and come back and get it later. So the actual query engine for Lua, for Sky, it's kind of cheating. We actually take a SkyQL, it's a query language. We take it, parse it out into AST, abstract syntax tree, and then we just generate Lua and just dump it into LuaJIT. And LuaJIT, it's a really cool tool. It basically compiles your Lua down to machine code. It's pretty rocking. So it was really easy to integrate. You have CGO, which is pretty nice. You get about half the speed of C, and some weird little edge case things you have to worry about. But overall, CGO is actually pretty nice to use. Then we moved over to LLVM, which is like a compiler technology. Like if you use Xcode, you're compiling with LLVM. And it's really fast, like screaming fast. It's really heavyweight, and it's really complicated. like the actual outputs you get when you compile down your stuff, you get this like intermediate representation, which is this weird mesh between like C and assembly language, and it's difficult to debug. So, my point isn't just, hey, go use C. And like, if that was in my talk, that would be a total cop-out. This is really a Go conference, it's not a C conference. So the point isn't just that, hey, use C, you're done. It's that you can use C. Like, you don't have to throw away all this work that's been done out there. But since we're doing a Go conference, we'll go to the fun stuff. Actual pure Go stuff. How do you optimize, that low-level stuff, and what kind of bottlenecks do you really hit? So I wrote a library called Bolt with what I think is a very awesome logo. And I'm not going to take all the credit for this. It was actually a port of another project called LMDB, which is it's just an embedded library for database. Now, it uses a really great architecture just as far as like a B+ tree and a memory map. And it's really pretty clean. So ported this over. It's a memory map file. And then it has great things like multi-version concurrency control. You have strong ACID transactions. And my favorite thing is you get zero copy reads. So it's memory mapped, and you literally just point to where in your data file these keys and values are. There's no copying over, which can be a huge overhead. So some of the things I really really learned getting into this is there's certain things that you can really optimize, like batching work together. When you actually write update keys in your database, the actual change in a value in a map somewhere is pretty easy. But there's all this work around, you have to update these points on a B tree. You have to go through and update metadata to point to a new B tree. You have to go through and write the data to disk and then sync to disk. There's all this overhead. And it's really it's amazing just how much it adds up. So I did some tests, and I don't usually do actual seconds or benchmarks. I like to give relative stuff to give people a good sense of relative performance. But for me, this is batch sizes. So I'm going through and inserting one record at first in a transaction, and then closing it, committing it, writing to disk. And if I go from 1, that's the baseline, going from 1 to 10, I can insert 9 times as many key value pairs. These are fairly small key value pairs. You move to 100 at a time, it's 45x. So it really just jumps, and then finally at 90x. Another thing that I actually don't see used very often, but is a really fascinating idea, is transaction coalescing. So you can actually this is good if you have users hitting your website, and they all have different requests coming in. If you have kind of a separate Go routine that opens a transaction and just takes in updates through a channel, you can go through and just pipe them into one single transaction and just periodically commit. You get a delay for each of your incoming requests. Maybe you commit every 100 milliseconds. You get a whole delay for each request, but you get higher throughput. So you can really handle a lot more. But you get this whole thing where everything either commits or it all rolls back. So it's kind of a trade-off. This is actually a huge problem I see, but I've had personally a lot. So encoding it can really just kill your performance. I love JSON as much as the next guy, but it is pretty slow. So if you actually get into it and actually start using JSON for everything, it can be just a huge bottleneck. And this is no slight against the JSON package in Go. I think it's pretty fast. I even wrote one called MegaJSON that's just, it's faster, but we generate all the parsers, compile time, and actually try to process the stuff at blazingly fast speed. And it's still only 2x. It's not even that much faster. So, the idea is, with JSON, you go through and you start looking at stuff like, if you want to parse out a string, you have to go one byte at a time to find the end of that string, to find that double quote. And then you can close it, and then you move on to the next thing. If you want to parse a number, you have to parse it out as base 10, convert to base 2. There's a lot of overhead in these little things. And you might have to do that millions of times for a couple megabytes for JSON. So you can use alternatives like Protobuf. There's also just a regular Protobuf library, and then Captain Proto is a lesser-known one, but it's blazing fast. There's not much you have to do to convert from the encoded version to your machine version. I feel bad. I don't know how to pronounce his name, but Albert, he is here. I don't know if you can raise your hand. Oh, over there. Albert's over there. He knows a lot about serialization. I'm sure you can talk your ear off. He did a talk on this and has some great stuff you can look at, comparing and contrasting all the encodings and marshallings. So, once you start getting into like these really low-level things and you want to start really playing around, you get into what some people might call bad ideas, but I like to call them crazy ideas, where you can really eke out that performance. I work a lot in analytics, so it's really about taking like tons and tons of records and just blowing through them as fast as humanly possible. So if you have this problem with encoding, the best way to improve the performance of encoding is to not encode at all. So I do not actually recommend this in most production systems, but you can direct map to your data file too. This is a fun thing I've been playing with lately, is where you can actually literally take a struct as it represents in memory and just put it into your database. Obviously, this is not usually recommended. So a few groans out there I can hear. But what you can do is you can actually find the size of the struct that you want. So we'll walk through this. You can make a byte slice of the size of your struct. You can then cast it using unsafe. Obviously, it's unsafe. And then you can go through and you can update that like it's a regular Go struct. And then down at the bottom, this is the bolt code, where the update starts a transaction and closes at the end of the function. And we're just going to put this value into a bucket. And then we can go through. We can actually take this byte slice. And then, so we'll walk through this. So the view right here actually starts a read-only transaction. So we'll grab that same bucket we had before, but make a cursor. So now with this cursor, we can just start from the beginning of the bucket and go through all the values in the database. And so each time we do that, we'll just cast to the type T. Does that make sense? So, it's definitely an unconventional way of doing things, but it really tells you about this low-level power of Go. Like if you really need something to go mine numbingly fast, you can drop down to some pretty low-level stuff. So instead of, a lot of us talk about processing speeds of 10,000 records a second or 100,000 records a second, you're not doing any decoding, encoding. You can insert a bunch of records. That's mostly limited by your disk, but you can read 20 million values a second and just put them into your struct. I mean, it's kind of ridiculously fast. Obviously, the con is you have a fixed struct layout. You have machine-specific endianness. It's just a bad idea. I mean, like people just tell you you're crazy. So generally don't do this, but I mean, it's good to kind of look at unconventional ways of doing things to see, how to do it faster. So when you think about it, like, talking about 10,000 rows a second or 100,000 rows a second, we get 3 billion operations per second from our CPUs. That's just one core. So, I mean, it shouldn't be crazy to eke out those 10 million, rows a second. I mean, there's a lot you can do with each of those little operations. So, whenever I do performance work, I try to think about it in different ways, but I think about it usually in layers. So you've heard of like Maslow's hierarchy of need. You have you worry about the things at the bottom first, like your physical self, your safety. If you're not safe, you don't care about self-actualization. That's a hard one to say. You don't care about the stuff at the top. So we're not talking about this. We're not talking about the hierarchy of need. We're talking about the hierarchy of speed. And in this sense, we're looking at, if you have a bunch of network I/O calls or you're going to different servers, your memory access pattern doesn't probably matter as much. You really want to kind of hone in at where on this pyramid you're really kind of wanting to optimize. So, and it's interesting too. Like you look at like a memory access. Excuse me. So if you look at memory access, we're talking about nanoseconds, like 3 nanoseconds to grab from like an L1 cache, L2 cache, that kind of area. Look at mutexes, we're talking tens of seconds. If you're talking memory allocation, hundreds of nanoseconds. If you're talking disk I/O, you get into like milliseconds, and then network I/O, you're talking, microseconds, and then milliseconds for network I/O. And these can be flipped around. It's just kind of a general guideline I kind of think of. So the moral of the story is really, Go can be really, really fast if you know how to optimize it and know kind of where to, tweak some things. So that's a general idea. I wanted to, have time for questions, and take any questions.
I think we have a question here in the back.
Hey, how's it going? I have 2 questions, actually. Yeah. So it's a memory map file, and I'm just curious, how does it perform? For the speed, it seems like you're optimizing the file cache of the operating system. So how does it perform if the amount of data you have is bigger than the memory on the box?
Okay, certainly. So the question, is asking if it goes bigger than memory that you have in your computer, how does it perform? Obviously, it drops off once you can't keep things in memory. You have to read from disk. You're just throttled by disk, essentially. But there's really a lot of power in the Linux caching strategy of moving stuff from disk to main memory, from main memory up to your L2 or L3 cache, and then finally up to L1 cache, and moving that in and out for you. I mean, there's certainly optimizations you can do to get around that kind of stuff, or to optimize in your own ways if you wanted to bring caches in. But as far as trying to keep things simple, and really ultimately when you're trying to write a database, like you don't look at features as being cool anymore. You're looking at them as like liabilities. Like they're scary. So I mean, you want to keep it as simple as humanly possible. So Bolt is only maybe 2,000 lines of code because it tries to keep everything bare bones and tries to keep it safe. So ultimately, it performs as well as your disk once you follow back onto disk. But I feel like it performs pretty well. I've had pretty good success.
Okay, and just another really quick one, which is if you run this on SSDs, does it kill you on like write amplification, or is it?
I mean, I haven't had poor experience with that so far, but I can't speak. I haven't had that experience so far, no.
You have a question over here.
Okay.
I'm going to go Stadium Beer Pass.
Thanks. Have you had a chance to compare this with the other Go wrappers for LMDB?
For LMDB, yeah. So there's GoMDB, which is the C wrapper. I've actually started out using the GoMDB, and it's a great package. One issue you really hit when you're doing that kind of, oh, sorry, what was that?
Performance.
Yeah, so specifically around performance, the biggest issue I actually hit was that every time it tries to interact with the underlying LMDB, LMDB is zero copy itself, but only when you use it directly from C. When you try to copy stuff into Go and have the actual support of byte slices, it has to actually allocate those every single time going in and out. So there's a lot of overhead I found with that. But otherwise, the library I feel like it's a well-done library. But performance-wise, I found better performance with Bolt.
Hi. I'm wondering, over here.
There you are. Okay.
I should stand up. I'm wondering when it comes to designing things like these little databases and stuff, if sort of you could speak a little bit to how you decided to design your APIs and how that might have effects on the performance of the actual underlying system.
Oh, sure. Okay, so when designing the API, I mean, a big thing for me has been to really construct it around well-known examples. So, I started asking around, like people like at React, like they have the concept of buckets inside of their database, and I asked them, where'd you get this term bucket? How common is that? Do people call it other things? I really try to make it very intuitive for people to understand that. As far as performance implications, as it stands right now, like when you want to go get, if you want to see like if there's a value in the database, you have to go get it to see if it's in there, and if it's not, then you have to go put, but it still has to like retraverse all that. There's definitely optimizations in that way, but I've definitely been very careful about trying to add too many methods and make it very complex around very unusual use cases. So there's a put right now, but I may add a put if not exist, go around that route, but try to keep it pretty straightforward. I mean, honestly, performance is a big deal, but personally for me, it's not the biggest deal. Actually, I find that on Twitter I get in a lot of arguments with people that just say, hey, this is the fastest thing ever, it's amazing over here, and then I say, well, but this thing is totally unusable over here. Why don't you just lose 10% of your performance, but you can actually understand what's going on. It's simple, and you can work with it. So I tend to lean away from the performance group in general, but I still feel like it's pretty performant. You can usually find performance in other ways, I find, as well. Any other questions? Cool. Thank you very much.